Yeah, thanks for the introduction, Jennifer. It's really nice when the talk before you motivates what you're going to talk about. So in anticipation of this, I basically don't really have that much motivation because I'm looking at the same problem that Yeva's looking at. So we're in the weak constraint 4D var case. I want to balance information with observations and background over a time window, and I'm allowing my model to be imperfect. So this is exactly the inexact constraint, the weak constraint objective function that we just saw. And skipping out some intermediate steps, we obtain the same saddle point formulation that Yeva just presented. And so if you aren't that interested in data assimilation, here's the linear algebra problem I'm going to be talking about today. And my motivation follows on nicely from what Yeva was talking about, and I'm going to be looking at preconditioners for this system here. And in particular, thinking about how can we better approximate this L term and this R term. So in this saddle point system, each of these matrices consists of kind of stacked blocks for each of the sub-windows of our main time window. And yeah, so I'm going to be focusing mainly on this R and this L. Okay, so again, the advantages of this saddle point system compared to the more standard objective function formulation is really this parallelizable nature, as Yeva said. And there have been some challenges associated with this formulation. So I'm going to talk mainly about numerical linear algebra challenges for the moment. But one challenge is that a lot of the saddle point research has been that the 1-1 block is hard to deal with and the 2-1 block is easy. And we've just heard that this is really not the case. And in fact, the 2-1 block is very hard. And sometimes the 1-1 block is also hard. And so this means we can't always consider what are the standard saddle point approaches, even though we are in a saddle point system. And in terms of preconditioners, this might mean, for example, that we definitely cannot invert this 2-1 block exactly, or we can, but we don't want to use it. And we probably also don't want to use the exact 1-1 block inverse. So that might mean we have to think slightly differently to how we have done previously. Okay, so here is the L matrix, and a kind of illustration is one of the reasons why we don't want to use the inverse of this exactly in our preconditioner is kind of hopefully apparent when you write out what the inverse is explicitly. So we have this block diagonal lower triangular matrix with identities on the diagonal, and then we kind of collect the models for the different times together. So we end up with this can be dense, and we also have these sequential operations where we have to compute the products of multiple models. And even if we are just doing matrix vector multiplications, we have to do a lot of them. So we want to avoid this. And as has been previously mentioned, there's been some approaches before, but the results haven't been that good, really. And so I'm just going to present these. So the kind of most commonly considered approximation is where we take L0 is this. And so what this is equivalent to is retaining that block diagonal identity and then just neglecting everything that was below the diagonal. So this is in fact the identity matrix, and so therefore maybe not a great preconditioner in terms of improving the spectrum, but it's really cheap to apply because we don't actually have to apply it. Another alternative I'm not really going to talk about here is kind of a similar idea where we keep the identity block and then we replace the M terms on the lower diagonal with minus the identity. And so when we compute the inverse of this, instead of all those products of M to M, M0 to Mn, we're just going to get products of the identity. And what you might notice for both of these is that they're not actually including any information about my operator M. And so we might expect that we could perhaps do a bit better in terms of improving the spectrum of L if we include some of that M information. But we really want to avoid having those really long products. And so is there kind of a middle ground there? And hopefully this is an answer. So the idea we're doing here is that we're going to keep some of the model information, but not all of it. And the way we choose what to keep and what to throw away is going to be with our parameter k. So I've drawn the idea here on the left. So for k is 3, which is in red, I'm going to keep my first two M blocks and then discard the third one. So I'm just going to replace this with 0. And then again, I'm going to keep the next two, replace this with 0, and keep going. And I can change my parameter. So if k is 4, that's blue. I keep the first 3, and then I throw away the fourth one. And so this is a nice idea, because if I go back here, if I do k is 3 and m2 is 0, anything that involves any product with M2 in it is just going to be 0. So all of this block here is just going to be replaced with zeros, and I don't have to evaluate these matrix products anymore. So that's exactly what you get if you compute the inverse in the case of k is 3. We get that the inverse's preconditioner is now block diagonal, and we can control how many products we have in this matrix, and that's controlled by our choice of parameter. So you can imagine that if we allow our parameter to increase, we're going to include more terms and we're going to have more matrix products. So we expect to see a trade-off between having a smaller choice of M is going to be cheaper, but we're keeping less information. But I'm not really going to talk about that today. So this seems like it could be a nice idea, but is it actually any good? So the first thing I'm going to do to assess whether this is sensible is think about the eigenvalues of my system. So firstly, I'm going to look at this product here, and the idea is that if Lm is a good preconditioner, then we'll expect that these eigenvalues to be close to 1. So I'm going to make some assumptions to make my life a bit easier. One is that instead of having different model operations at each subwindow, I'm just going to keep them all the same. And then I'm also going to assume that this M is symmetric and has eigenvalues in the range of -1 and 1. And so if I do that, I can bound the eigenvalues of LL transpose above by 4. So we can also think of this as the eigenvalues of L0 inverse LL transpose L0 inverse transpose, because the identity won't change anything. So if I do a kind of similar approach, but using my new preconditioner, so I'm going to have k is 3, skipping every third block, we can prove that the largest eigenvalue of this product is 8. And so both of these are independent of the number of subwindows we have, which is good. But one thing we'll notice is that 8 is larger than 4. And so actually my improved preconditioner, the maximum bound is larger than if I did nothing. So that doesn't look very hopeful, but that's just the extreme cases. What about the rest of the eigenvalues? And so the good news is that I can, with my new preconditioner, because I'm actually including model information, I'm going to have lots of eigenvalues that are actually the identity, and we can say a priori how many unit eigenvalues we expect. So this is a slightly more complicated expression, and it depends on S is the size of M. So again, M is symmetric and has these constraints on the eigenvalues. So if I have k is 3, skipping every third block, and I have at least 3 subwindows, then this product has 2 plus I times by S unit eigenvalues. So I is this expression here, which looks a bit complicated, and I've got some results a bit later. But basically this will increase with n, not monotonically. But that means as we have more subwindows, we expect that we're going to get more unit eigenvalues. And this was not the case if we just use the identity preconditioner. So although we're going to get some extreme values that are slightly bigger, we're going to get a lot of unit eigenvalues. And hopefully this will mean that our new preconditioner is actually helpful and it results in improved convergence. Okay, so to illustrate this in a more concrete way, I've got some kind of quite straightforward experiments. So here my model is going to be the same every time step. It's the heat equation with 0 Dirichlet boundary conditions. So this satisfies all my assumptions of symmetry and my bounded eigenvalues. For my other data assimilation terms, the B and the Q, which was in that 1-1 block of D, they're going to have a spatial structure. And we're going to have R is going to have a block structure with more random entries. And I'll maybe explain a bit more about that later. But importantly, it's going to have information, significant information away from the diagonal. And then I'm going to observe half of the variables every time, but it's going to be random which one I observe. And for these matrices, I'm just going to have the same one every time and just stack them. Okay. So here's a table that explains what happens if I increase the number of subwindows for a problem. So here my state is 500 and I'm observing 250 observations. So this first column here tells us how many unit eigenvalues we'd expect. So this times 500 in this case will give us the number of unit eigenvalues. So you can see as we increase the number of blocks, we're increasing the number of unit eigenvalues we expect to see. And so this is kind of between 40 and 60% of the eigenvalues are going to be equal to 1 exactly. So that's really nice. That, hopefully that means that our eigenvalue will perform well in practice. We've also got this upper bound. So I said before that 8 was the upper bound for any choice of n. For small choices of n, we can actually do a bit better. But we can see that these bounds are bigger than the 4 we got for the LL transpose case. Looking at some computed eigenvalues to see if our bounds are any good, we see that our bounds are maybe a bit pessimistic, but quite reasonable. And again, for if we have 5 or more windows, the largest eigenvalue numerically exceeds the bound on the LL transpose. But what this is saying is that as we increase the number of sub-windows, although we're massively increasing the dimension of our matrix, we don't expect the upper bound to blow up at all, and we expect there to be a significant number of unit eigenvalues. Okay, so moving on to the observation error covariance matrix. So traditionally, it's been assumed that R is either diagonal or really easy to invert, and actually there's a lot of realistic examples where that's not the case, where R is dense and has a really high condition number. And so we want to include that information, but inverting R exactly is probably not possible. And so what we're going to do is consider 3 quite kind of obvious choices at first. So the first case, we're just going to approximate R with a block diagonal and just split it into approximately equally sized blocks. So in my numerical example, this will mean throwing away a lot of that off-diagonal information. My other 2 examples are going to keep more of that information and change the eigenvalues of R. And so the first method, we just increase all of the eigenvalues by a constant. And then the second example, we have a threshold, and if anything smaller than the threshold, we increase those small eigenvalues. And importantly, both of these methods can actually be done in a heuristic way without computing the full eigendecomposition of a matrix. And so the nice thing about these second two approaches is that similarly to what we did in the case for L, we can bound the eigenvalues of the preconditioner and the original R matrix. And as we'd expect, if we let delta and t be really big, so we make lots of changes, we'd expect our eigenvalues of this product to be far away from 1. And if we keep them quite small, we expect it to be a better preconditioner in the sense of more eigenvalues closer to 1. Okay, so now let's see if these ideas are actually any good in practice. Some numerical experiments. We're using the same framework I introduced a few slides ago, and I'm going to use a preconditioner that is a block diagonal structure. So this is a kind of standard approach. So we've got our one block here. So I'm going to use the exact D and use one of my new R approximations. And then in the 2-2 block, we've got a Schur complement approximation. And this has 2 levels of approximation here. One is there should be a term that involves H and R, which I'm completely neglecting. And the second one is I'm using my new approximation for L in here. And again, I'm using my exact D. And this is quite common in data simulation problems. So I'm going to compare just using the identity with our new preconditioner. And then as a test for the R approximation, I'm just going to use the diagonal of R. And I'm going to do some experiments using MinRes. Going to keep 5 sub-windows and increase the dimension of my and see how this changes. Okay, so in these figures, on the top we've got the wall clock time, and at the bottom we've got the iterations to reach convergence. And the solid lines are a new preconditioner for L, and the dashed lines are using the identity, and then each color is a different choice for R. And we can see a couple of things. One is that for all of the choices of R except the blue one, the solid line is lower down than the dashed line. So this means that our new preconditioner for L is better both in terms of wall clock time and in terms of iterations than just using the identity. So that's really promising. And the other thing is that our new choices of R, so the red, the black, and the cyan, are better than the dark blue, which is just using the diagonal. And actually, in terms of wall clock time, there's not that much difference between using an improved approximation for L if we just use a really rubbish preconditioner for R. So this really emphasizes that it's quite important to account for the R matrix in this framework, which hasn't really been considered that much before. Yeah, so this shows that our new methods are quite promising. Obviously, in the black and the cyan lines, there are some parameters to fiddle with, and I've just done this heuristically. But this shows that this approach hopefully has some merit. To conclude, we've proposed some new preconditioners for the saddle point formulation of weak-constraint 4D bar. Our new method for L incorporates model information, which has been shown to be useful. We've got multiple approaches to precondition R when it has correlated features, and we can bound the eigenvalues of these terms and show that there is some benefit to these approaches. The iterations and the walk-up time are both improved compared to the previous standard choice of preconditioners. Moving forward, we've got some bounds on the preconditioned saddle point system as a whole, but they're quite pessimistic, so we'd like to improve those. One thing I mentioned in my abstract that I haven't talked about is parallelizable approximations to R. So we had that block, naive block approach, but it wasn't very good. So can we do better there? And the experiments I presented today were quite small and for quite a simple problem. So can we do something more realistic and show that our method is competitive? Again, our new preconditioners have parallelizable aspects in them, but currently all the experiments are in serial. So that's probably something we should think about there. So that's the end of the talk, and I'm happy to take any questions.
Thank you very much, Jemima. Okay, we've got a question from Andy Wathen in Oxford. Page 9, your theorem has lots of 3s in it.
Yes.
Do these become 4s for k equal to 4?
So it doesn't quite become 4. You can derive a similar expression, I think, but you don't just simply replace the 3 with the 4, unfortunately, but you can get something quite similar. Partly because when you precondition, you get k minus 1, that identity block. So this becomes a 3, and then you kind of have to get rid of that 1 from here. So a similar thing, but not exactly this expression.
Okay. Does anybody else have any questions? So do you envisage it being a feasible method for k relatively small, presumably?
Yes. Yeah. So we think that, some numerical tests in this framework, I've tried 3 and 4, and they both, there's not that much improvement with 4 compared to 3. So maybe 3 would be enough. I think probably it would depend on your PDE.
Yes. And Yeva has asked a very pertinent question. Did you compare your preconditioners with not using any preconditioning?
Yes, the not using any preconditioning was really bad. Like, it didn't even converge most of the time in the maximum number of iterations I'd set.
Yes.
So it is really important to precondition.
Yes. And how reasonable an approximation is mi equal to m for all I?
I'm not sure. Well, for simple systems, it's reasonable. For more thinking of like numerical weather prediction, probably there would. I think it's reasonable that they wouldn't be that different, but there would be some differences. So I think the idea is that probably the exact bounds and the theory wouldn't be expected to hold for a very big, complicated problem. But the hope is that some of the conclusions and heuristics would hold. So, maybe you wouldn't get exactly identity eigenvalues, but you might get close to 1, for example, I think is the hope.
Yeah. And final question from Anthony Weaver. Or comment, he is thinking that your preconditioner uses d to the minus 1,
yeah,
and he's not convinced that d to the minus 1 is thinks that's generally unavailable in operational data assimilation.
Yeah, that's probably fair. I mean, you could also include a term where you approximate d as well. So that would, to remind people, that came in here. So we're using it in the Schur complement term. So you could also add an additional approximation there. And our bounds on the full preconditioned system allow for that. But we haven't considered that here yet. But that's a very fair comment.